I've spoken about photoresistors before, and I've shown you how to use one as an optocoupler, but I've only spoken about how you can use one to actually sense light, which technically is its direct purpose. So let's go ahead and do that now. There are several different ways you can wire one up, but I'm going to use it as a voltage divider, which is the simplest and easiest way, which allows it to be not only the input to a microcontroller pin, so you can read a voltage and interpret a brightness from it, such as with an Arduino, but also it allows you to drive a transistor, so you could use the brightness sensor to turn on and off something else if you wanted. The circuit is incredibly simple. A power source, your photoresistor, a fixed value resistor, and that's it. It is a voltage divider, so you will read the voltage from here. This is the voltage that you would connect to your transistor base or your microcontroller input pin. When the photoresistor is receiving no light at all, it has an incredibly high resistance, not infinite, but well into the mega ohm range. So, as we know, a series resistance, it's proportional. So you have a resistor and a resistor. The total resistance, R1 plus R2, drops the whole voltage of the power, Kirchhoff's voltage law, and it's proportional. If we call this R1 and R2, the combined resistance is R1 plus R2, naturally, and then the ratio could be either one of these. Let's say R1. This is effectively giving us a percentage. If R1 was 100 ohms and R2 was 300 ohms, so let's say that. R1 is 100 ohms, R2 is 300. So that gives us 100 over 400. 300 plus 100 is 400. So that means R1 is dropping 25% because 100 divided by 400 is 1 over 4, 1/4, 0.25, times 100 gives you 25%. So this ratio is effectively the percentage. If we times 100, if you want, that's how you get a percentage out of it. It's just times 100, and that's the percent. This is the percentage of the series voltage drop by the resistor. If we change it to R2, then it becomes 300 over 400, which is 75%. We add those two together, we get 100%, because that's the whole thing. You'll see this a lot. Anywhere voltage dividers are used, if you ever see a bunch of resistances added together, and you're dividing that into one resistance, that's what they're doing. They have a series of resistors, and they are figuring out how much resistance each one of them drops. It's just a ratio. So, you can see, if this has a gigantic freaking resistance, and this is just some little resistor, even 10K, 100K little, but still little-ish, not like this, not in the mega ohms, then what happens is, this plus this is some big number, and this is so much bigger than this, right? So, big number over big number plus little number. That's pretty close to 1. That's nearly 100%. The biggest resistor is dropping most of the voltage with a little bit left over here. So, if this is getting no light and it has a high resistance, then if you sample here, you're getting a voltage close to the negative side, because most of the drop from the positive is here. So you're getting something near zero. And if you size this resistor correctly, you can make sure that's not enough to forward bias a transistor, or you can just read it and know whatever number it is. If you're using a microcontroller pin, you just get a number. When the photoresistor is receiving a good amount of light, it starts dropping in resistance into the kilo ohms. If you have a huge light on it, it can drop down to the single-digit resistance, but that would be like a pinpoint laser. Generally, from what I've seen, if you use a nice strong flashlight, you can get into the, 100 ohm or less, but normal light like this room would probably be, a few thousand ohms. So you size this resistor properly based on the amount of light you want to detect, and now you have this one is dropping equal resistance, or even less. If you have this be a 10K, then any appreciable light is going to make this one smaller. So this might be 2 volts, 3 volts, 4 volts even, with a lot of light, and depending on how much you size this. So basically, all you have to do is figure out the size of this, and we're going to use a potentiometer to do it. I will set my power supply to 5 volts. Let's go ahead and set it on 10 milliamps. Let me get out a photoresistor. Let me confirm that the photoresistor is working. So if I measure across it, the resistance, right now we're getting 2,500 ohms. If I shadow it, it goes way high. So it's working. So now we create our simple circuit. From positive power into the photoresistor. Now I need a potentiometer. I'm going to choose a nice big one. You almost witnessed quite a mess. Let's say 200,000 ohms, 200 kilo ohms. So I'll put this in my breadboard, put it there. I would use my breakout board, but those only go up to 10, which is suitable for pretty much every purpose except this one. So let's confirm, always confirm. You don't want to spend 18 years diagnosing what's gone wrong when you can just check each step quickly. The resistance across this potentiometer is about 200 kilo ohms. Good enough. So now we know that's working. So I connect the other end of the photoresistor into one side of the potentiometer. Now I'm using the potentiometer as a variable resistor, so we will use only the middle pin and one pin on one side. So I'll connect the middle pin out to negative power. Now I'm going to simulate a high impedance measurement pin on a microcontroller with a 10 mega ohm resistor. For those of you following along at home, 10 mega ohms is a lot of mega ohms, though it's actually lower than the impedance of an input pin probably would be. I could add 2 of these in series if I wanted, but 10 will be enough for now. So now I will connect a wire from between the photoresistor and the fixed resistor, well, the variable resistor here, but it would be a fixed resistor, across this resistor, and from there out to negative as well. And then we'll measure across that resistor. And let me get it off of the resistor setting before I do anything, though I'm sure this thing has fuses just in case, but let's get it onto volts. So right now, we're getting 4.87, 4.88 volts. If I shade it, it goes down to 3. If I shade it better, I can get it all the way down below 1/10 of a volt. Right now it's at 50, 40, let's even go into millivolts, shade it mostly well, down to 20 millivolts, I think we get the point. So in the darkness, the way we have it set up, it's going to turn off whatever it's connected to. Now, here's the thing. Let me start adjusting this potentiometer and see what happens. So I turned up the potentiometer and we're now getting 0 volts. Let me turn it back down. So you can see that this potentiometer is stealing a fair bit of the voltage if I turn it high enough. This is how you adjust your high end. So what effect does the size of the resistor have? First of all, the bigger the resistor, the slower the thing is to respond to a change. But on a human time scale, it's still really fast. And also, the photoresistor already is huge on one end when it's getting no light, so that's not much of a concern. But mostly it affects your resolution. The bigger the resistor, the less power is dissipated, so it's easier on your battery if you have a portable device. And it also generates less heat. But the more, as you saw, that was the high end. The low end is going to be 0, but the high end is going to go down and down and down closer to 0, the bigger your fixed resistor is. So if you have that fixed resistor too big, then even when the photoresistor is getting light, it might not be enough to pull the voltage up to turn on your transistor. Or if you're trying to measure actually about how much light, not just is there light, but trying to measure how much, the bigger your resistor, the lower your resolution, because observe again, when I'm shading it, it's going to go down near to 0, no matter what this potentiometer is on. If I turn it all the way to one end, let me use a better screwdriver for this. If I turn it about all the way to one end, then when we shade it, it will slowly, let me shade better, it will slowly go down, but it will indeed go down. See the response time. So actually, this does have quite an effect. But if we turn it all the way to the other way, then it's already 0. 0.1, if I shade it, bring it back out, you can see it's going between 0.0 and 0.1. Let's have a smaller measurement here. So right now it's only 10 or so millivolts, and I shade it and it goes down to 0.2 millivolts, back up to 10. But if I put the potentiometer somewhere more reasonable, when it's in the light, let's say about 3.33 is enough. Then we shade it, it'll go down, bring it back up, and it's faster. So basically now you'll be measuring a number on your microcontroller pin that's 3.3 some in bright light, and in shadow it'll be like 1.6, darker shadow 0.8, and then it'll go down to 0. Let's say we use a little bit bigger, just a bit. So now I get, in that same bright light, we get 1.6 or so. Then in the shadow, we get 0.5, better shadow goes down 0.09. So the range, you've got bright light, dim light, almost no light, and that's getting compressed. If you compress it too much, you can't tell the difference. It might just be a measuring error. So you got to get it big enough that you can tell. If you just want to tell if there's light or not, you can have a really big resistor because it's going to be far enough from 0. But let's say you need to know if the light is really bright so you can turn on your backlight really high, and if it's dim, you turn it on somewhat, and if it's really dark, you turn the backlight almost completely off. Then you need enough of a range to be able to do that reliably. And that's just going to depend on your application. So use a potentiometer to decide, okay, for my application, for my application, use a smaller potentiometer so you don't have to mince so much. But let's just say there, 2.8. 2.8 to 0 gives me enough of a range to say, hey, I can measure that, I can work with that, I get what I need. So then all you do is disconnect the circuit and measure whatever your potentiometer is at. So in this case, you measure a middle pin and the side pin, the same two pins you were using before, and you see it's about 3.1 kilo ohms. So then you go in your box and you say, okay, 3.1 kilo ohms looked about right. Let's look in my box. 27, 3.9, 2.7, 3.3. So now you decide 2.7 or 3.3. Do you want a little less range or a little more power dissipation? And you just pick which one. And that is the art of selecting resistors. Step 1, figure out what value you need. Step 2, figure out the two closest values you actually have. Step 3, decide which side the error is okay on. A little more current, a little less current, whichever is less harmful. A nice and simple circuit from positive power through photoresistor, through fixed resistor to the negative power, and measure between the resistors as a voltage divider. Remember that the output of a voltage divider is affected by the load. That load, if it's lower resistance, is going to change the numbers because it ends up being a parallel resistance. So it changes the effective resistance at the divider. Super high impedance, the bigger the resistor of the load, such as an input pin to a microcontroller, is going to be large enough that it won't affect the divider appreciably. So if you're talking 20 mega ohms on your load, then don't worry about it. It's going to have an effect if you're using it to drive something like a BJT transistor. Yes, I just said bipolar junction transistor. Let's not worry about that. So in that case, you'll want to have the transistor in the circuit and then modify your fixed resistor as a potentiometer or variable resistor, whatever you have, until it turns the transistor on and off at the right point, and then just write down whatever number that was. So while you go do that, I'll be seeing you.